Okay, let's get started. Thanks everyone for being here. I know it's Thanksgiving week, and as you can see, not many of you are here. So it's getting colder, and everyone's mood seems to be a little low energy. So I'll try and have a low-key type of lecture today. I will try to end a little bit early, and we'll see how this goes. But we have a pretty small group, so feel free to ask questions, and we can try and have this be a little bit more intimate than it usually is. So we're in lecture 5 of module 3. We basically have this lecture and 2 more lectures to go before the class ends. And basically now, today's lecture is where we're going to start picking up into even more slightly advanced machine learning algorithms. And what we're going to do is we're going to introduce this algorithm called orthogonal matching pursuit, which is an algorithm that can be used to get around this n equations and n unknowns barrier. So far we've seen that, if you have n unknowns, you need at least n equations to be able to solve them. Sometimes if they're noisy equations, you need even more than n equations, right? This is what least squares has been doing. But turns out, under certain cases, if you have certain structure in your system, you can really pull information out of the data, and you can break this n equations, n unknowns barrier. And the very cool thing about this is that this very, powerful idea is something that is 100% accessible to you in your first year here at Cal. So it's a pretty exciting idea, and we'll cover it basically over this lecture and the next lecture. Before I get started into that, I got a bunch of questions at the end of last lecture about the proof that we did at the end of lecture. So would people like for me to just talk through it once more really quickly so that I'm seeing a lot of nodding, so I'll go ahead and do that. And I'll give an example for this as well. So today's plan is, just finishing up least squares. And, think about this. Is A transpose A invertible? And we saw the answer to that last time. We said that, to understand if A transpose A is invertible, we don't have to look at this matrix A transpose A. We can just look at the columns of matrix A. If they are linearly independent, then basically we're good, right? So we're going to talk a little bit about this. I'll show you an example of how A transpose A might not be invertible. And then we'll move finally to talking about orthogonal matching pursuit. Okay. So last lecture, we proved the following theorem. We said that the null space of A transpose A is equal to the null space of A. Right? We said that, we want to understand the null space of A transpose A because null space of A transpose A is basically telling us about the invertibility of A transpose A, right? If A transpose A is invertible, then what is the null space of A transpose A? 0, right? It's just the 0 vector. If, on the other hand, A transpose A was not invertible, then it would have a non-trivial null space, right? So now we want to compare this null space of A transpose A to the null space of A. Can we just think about whether or not A is invertible? What are the dimensions of A, right? Remember, A is a matrix that looks like this. It's an n by m matrix, but n is much, much bigger than m. So we have a lot more, like it's not a square matrix, right? And we only defined inverses for square matrices. So we can't just say, well, let's just check whether or not A is invertible. The whole reason we ended up doing least squares partly was that, well, we have more equations than we have unknowns. We know that these are noisy. So we want to, use these extra equations to get at a better estimate, right? We can't just do an inversion. So A is not square, so we can't just look at the inverse of A, which is why we want to compare to the null space of A, right? And what we basically want to see, and we know that the null space of A is non-trivial if columns of A are linearly dependent. Right? What does it mean for the null space of A to be non-trivial? It means that basically if A times x is equal to 0 and x is not equal to 0, then x is in the null space, right? It's a non-trivial null space if I find such an x. But A times x, remember, is just a linear combination of the columns, right? This is if I think of the elements of x1, x being x1, x2, xn, and the columns of A being a1, a2, an, this is just a linear combination of the columns. So looking at the null space of A is basically equivalent to looking at, whether or not the columns of A are linearly independent or dependent, right? We did all of this in Module 1. It's worth quickly reviewing that at some point. Make sure you understand the connection between linear dependence, independence of the columns, and the null space of A. Okay? So is everyone clear on why we were examining the null spaces of A transpose A and the null space of A? Does everyone see why this is connected to the invertibility of A transpose A? Yeah? Do I see some nods at the back? Any questions? Okay, great. So now let's go to try and actually proving this. So what did we do last time, right? We said that we wanted to prove that these two things are equal. And when we have two things that we want to show, these are two sets, right? These are two vector spaces. So we need to show that every element in this null space is an element of this null space, and every element in this other null space is an element of the first null space, right? This is what we need to show. So let's just write that out. The first thing we need to show is that if some vector v belongs to the null space of A, then v also belongs to the null space of A transpose A. And the second thing we need to show is that if there's some w that belongs to the null space of A transpose A, then w belongs to the null space of A. Okay, I'm going to pause here. Is it clear to everyone why we need to prove both of these things? Okay, take a minute, make sure that you're comfortable with why we have to prove these two things. We've done this proof last time a little bit, so make sure that, try to do it again on your own. Like, just take a minute, make sure you understand what direction we're going in, talk to your neighbor, get comfortable with this again. Remind yourself of what happened next lecture, and then we'll proceed. I really want to make sure that we all are together in this when we're doing this proof. It's a smaller class. There's more opportunity to ask questions. Use it. Okay, how many people have refreshed their memory of what we did last time? No one? Everyone forgot? Or no one wants to proceed? Everyone just wants to go home? I understand. We're gonna make this easy. Not gonna do anything super hard today. We're just gonna, friendly lecture. So, any questions on why there's two statements? Yeah. Yeah, okay, so one way to think about it is to say that, if this, just drawing a crude picture, if this is one of the vector spaces, let's say this circle, which obviously a vector space wouldn't be depicted as a circle, but let's just pretend. And I want to say that this other thing is exactly the same. I want to make sure that, when I think about the second vector space, everything in here is in here, and everything in here is in here. I don't want to have any stuff that's in the pink set but not in the black set. And I don't want to have any stuff that's in the black set but it's not in the pink set, right? So, in the first thing we're saying, if V belongs to the pink set, it also belongs to the black set, right? But it's possible to then have a picture. If you just showed the first thing, you could have a picture like this, and that would be true. Right? When you show both of these, you can say that, well, it's not possible for just the pink to be inside the black or the other way around. They have to be exactly equal. So this is why we need to prove both directions. This is a slippery thing, so make sure you understand. And feel free to ask questions. But, okay, so now let's start with trying to prove one. And so now, if we have an if, and then we have a then, right? So, if this, then that. So, let's assume that V belongs to the null space of A. We are given this, right? So we know this. We know that this is true. What does it mean for V to belong to the null space of A? We can write it as A times V equal to 0, right? V belongs to the null space means this equation is true, right? I'm just writing out the definition. What do I want? I want to have V belonging to the null space of A transpose A, right? This means I want to have A transpose A times V is equal to 0. Right? This is what I want to get. So how do I manipulate this to look like this? I'm going to multiply by A transpose, right? So this is a natural step. So multiply by A transpose. We're going to get A transpose A, V. And if I multiply this by A transpose, I'm going to get this equal to A transpose 0, right? Multiplying both sides. But A transpose times 0 is equal to 0. Therefore, V must belong to the null space of A transpose A. Because A transpose A times V gives me 0, means that V must be in the null space. Right? Great. So this is the more straightforward part of the proof. The second part of the proof is where I got a lot of questions after class. And before doing the second part of the proof, I just wanted to remind people of a property of transposes that you may or may not have seen before. So, if I have a matrix A and a matrix B, and I take A times B, and I consider A times B transpose, this is equal to B transpose A transpose. What happens when you take the transpose is you flip the order of the multiplication. And why does that happen? I got some questions about this after the last lecture. But if you think about it, let's think of A as an n by m matrix and B as an m by k matrix. Okay? So AB, what is the dimension of AB? N by k, right? What is the dimension of A transpose? A transpose is m by n, right? And B transpose is going to be k by m, right? So can I even multiply A transpose times B transpose? It's not even a valid multiplication, right? So if I want to look at the dimensions of B transpose A transpose, this is basically k by m times m by k. So this again gives me a k by n, right? And now if I think about AB whole transpose, the dimensions of this are also k by n, right? So these dimensions match up, right? That's one way to remember this. I highly recommend that you all prove this rigorously for a simple 2x2 example. Choose A is equal to A11, A12, A21, A22. B is equal to B11, B12, B21, B22. Compute out explicitly AB transpose and B transpose A transpose. And do the multiplication both ways and see that this actually works out. Okay? Basically, when you do that, you'll see that it's fundamentally related to this property of matrix multiplication about how we, take, when you do A times B, we take this row times this column, but transposes are basically flipping the rows and the columns. And so when you do this multiplication, things flip around. You can prove this out rigorously for, any arbitrary matrices of any dimensions, but just to convince yourself, make sure that you can verify it and prove it for the 2x2 case. Okay? It's a good exercise worth doing. But it's a property that you should all know, and so if you haven't come across this so far, make sure you know this. But I want to now use this property in our proof. So we now want to say that if this W belongs to null space of A transpose A. So let's say we're given that W belongs to null space of A transpose A, and we want to show that W belongs to the null space of A. Right? So if I know W belongs to the null space of A transpose A, I can write this as A transpose A W equal to 0. So ideally, wouldn't one want to do an argument exactly like the one above? That would be a natural thing that we would try to do, right? So what would happen? What would we need to be able to do to make that argument work? Someone else, yeah. We would need to somehow cancel A transpose, right? We would need to be able to invert A transpose. Right? If we had an A transpose inverse, we could potentially multiply both sides by it. But is A transpose a square matrix? So can we multiply both sides by A transpose inverse? No, because it doesn't necessarily exist. Right? So that's why we can't do the straightforward style of argument that we did earlier. Right? It's not because we want to just have complicated proofs for the fun of it. it's that the technique that we would want to make work doesn't work. And so we're going to try a different idea. So I'm going to do the proof a slightly different way than I did last time. It's essentially the same argument, but a slightly different notation to give you a different flavor, and hopefully that might answer some of your questions. But I want to basically show that A times W is equal to 0, right? So what are the dimensions of A times W? Is it a matrix or a vector? It's a vector, right? So if I want to show that a vector is 0, so AW equal to 0 means I want to show a vector is 0. Are there other ways of showing a vector is 0 other than basically showing that every single element is 0? Yeah, at the back? Its magnitude is 0, right? If we can understand the magnitude of the vector, the only vector that has 0 magnitude is the 0 vector itself. So if we consider the magnitude of AW, and let's consider the magnitude of AW squared, just because if a number is 0, its square is also 0. So if I have now AW squared, I can write this as an inner product, right? The magnitude of a vector is exactly the inner product. What is this inner product? This is AW transpose AW. Now I can use my transpose property to write this as W transpose A transpose A W. And now what do I have? Are people on this side with me? I write on that side, so I end up being on that side of the classroom more often, but you're good? Okay. So we have A transpose A W here, but what do we know about A transpose AW? This is equal to 0, right? Therefore, we can now say that norm of AW squared must be 0. But what does this mean? The only way this is possible is if AW itself is the 0 vector. And then what this gives us is that, therefore, W must belong to the null space of A. Are there any questions here about how we got to this point? This is a different kind of proof. You have not seen this type of proof yet, right? It's basically, it's saying, well, I don't have the object. I can't manipulate AW, which is the object I want. So let me consider a related thing, which is the norm of that vector instead of that vector itself, and try to manipulate that because it's slightly easier for me to manipulate. Any questions? Okay, should I move on? Okay, great. Yes, question? Absolutely, great. Thank you for asking a question. Okay, so we have W transpose AW is equal, right? So this inner product, I just said, well, X, inner product of two vectors, you take the transpose of the first vector and the second vector, right? So I'm just using this fact that inner product XY is equal to X transpose Y, right? So I'm just taking the transpose of the first vector and then the second vector. Now, I have AB transpose is equal to B transpose A transpose. So AW transpose, I had to flip the order, is W transpose A transpose. Right? And I just have this AW here. But now I can use the fact that matrix multiplication is associative. And instead of thinking of W transpose A transpose, so if I write this out in one more step, this is W transpose A transpose times AW. But I can write this out as W transpose times A transpose AW. Right? I'm just changing the order of the multiplication. But what do I know about A transpose A times W? It's 0 because W is in the null space of A transpose A. That's how I got that step. Does that help? Okay. Yes, question? The next step, so great, excellent question. So you're good to having the norm of this AW being equal to 0? That's fine, right? From here to here is good? Okay. So now we have the norm of a vector. There's some vector. AW is some vector somewhere, and its magnitude is 0. Right? When we look at all of the different vectors, is it possible for a vector to have a non-zero element in it and have its magnitude be equal to 0? The magnitude is the sum of squares, right? So it's always the sum of positive entries. So the only way that a vector can have its magnitude be 0 is if every single entry was 0. Because basically I can, let me write this here. If, let's consider x, norm of x squared, is equal to x1 squared plus x2 squared plus xn squared, right? If I tell you, if this is equal to 0, I know x1 squared must be greater than or equal to 0, x2 squared must be greater than or equal to 0, xn squared must be greater than or equal to 0. Right? So the smallest value this can be is 0. This can never go, none of these can be negative. So how do you have a bunch of numbers add up to 0? The only option is for every single one of them to be 0. So, therefore, x1 equal to 0, x2 equal to 0, xn equal to 0. Oh, why can't numbers be negative? Good question. So what if x1 was equal to minus 1? x1 squared is plus 1. Right? Because they're squares, they can never be less than 0. That's why they can't cancel each other out. Yeah?
But if we know that like AW gives us 0, cool, but like we don't know that the A transpose is, how do you know that A transpose multiplied by that is still 0?
So right now I'm just trying to show that AW is 0. I'm assuming that A transpose A is 0, and I want to show that AW is 0. So I'm assuming that this is told to me, because I know W belongs to the null space of A transpose A. So I'm told this, I want to show this. Here, I'm told this other thing, I want to show this other thing. These are all excellent questions. Like, thank you for asking them. I wish we had a smaller class that we could actually have these kinds of discussions in every lecture. Yes? Okay, so the question is, what's going on here? So if we were to write this out as an explicit theorem statement, we could say, if the norm of a vector x squared is equal to 0, then vector x is exactly the 0 vector. That's what it's saying. And why is this true? It's saying that, well, the norm of a vector x, let's say x has these components, x1, x2, all the way up to xn. The norm is exactly just the sum of the squares of the element, right? And so What are potential values for x1 squared? There's 1, 2, 3, 4, 8,000, 8 million, whatever you want. Can x1 squared ever be equal to -1? Right? Because xi's are real numbers. We're not allowing imaginary numbers here in our vectors. So, if they want all of these things to add up to 0, if any one of these was not 0, there's nothing else can cancel it out, right? So every single one of them has to be 0. Does that help? Okay, great. Other questions? Okay, should we move on? Okay, great. So we've talked basically about the connection between the columns of A. Columns of A and invertibility of A transpose A. But why should we care? When does this show up, right? This is a bunch of math that we did. Why should an engineer care about this? And so for this, let's go back to the trilateration example. I don't want to derive things out again, but if you go back to the third lecture in this module, do you remember this setup that we did? Where we had the 3 beacons, A, B, C. We measured distances from them, and then we got out these equations, right? We got out this system of equations. Okay? So let's consider a specific setup for the trilateration problem. Let's say the first beacon, beacon A, was put at 0. Okay? Let's say beacon B was put somewhere. Let's say B is equal to B. Let's say C was put at beta times B. Okay? And let's say, let's just stop there actually. So I had 3 beacons, and I put them in this particular way. So let's say if I draw a picture here, I have a picture here. A is at the 0 vector. Let's say this is vector B. And so this is my beacon A, this is my beacon B, and this is my beacon C, and C is equal to beta times B. What does it mean for C to be equal to beta times B? It just means that it's a multiple, right? So what is true about all of these beacons, A, B, and C? They're collinear, right? They're on a line. Okay, so let's observe this, and let's, just do our trilateration. So here we have the equation 2 B transpose minus A transpose is equal to, or C transpose minus A transpose, this is equal to D1 squared minus D2 squared minus norm A squared plus norm B squared. And this is D1 squared minus D2 squared minus norm A squared plus norm C squared. Remember, everything on this side, all of these quantities are known to us, right? We know the locations of the beacons, and we know the distance measurements. Let's simplify the right-hand side. So if I think about B transpose minus A transpose, this is just equal to, if A transpose is just 0, if A is put at the 0 vector, what is B transpose minus A transpose? Just B transpose, right? A is 0. So I subtract the 0 vector from something, well, I just have B transpose, right? What about C transpose minus A transpose? It's also just C transpose. And what is C transpose actually equal to? C transpose is actually B transpose, this beta, which is a scalar, times B transpose. So let's make it even simpler. Let's say beta is equal to 2. Right? This is just twice as far. Let's just say 2. So now, when I look at the columns of this matrix, let's say this vector B had the following components, B1, B2. This is basically B1, B2, 2B1, 2B2. Right? B is a vector in two-dimensional space. It has two components, B1 and B2. And I'm just substituting them in here. So what is true of this matrix now? What about the columns? Is the first column a multiple of the second column? Yes, right? The columns are linearly dependent. But this is the matrix that we were using to set up the least squares equation for our entire GPS problem. So is A invertible here? If this is my A matrix, or let's say, are columns of A linearly independent? The answer is no. Right? So therefore, is A transpose A invertible? The answer is no. So what is this setup that we're seeing here? We have the first beacon at the origin, the second beacon, and the third beacon all in a line, right? So let's try and draw out this picture. Let's say we had basically this circle around the first beacon, and we had a circle around the second beacon. Right? Now when I draw this C, let's say from this third beacon I have this distance, and I have the following circle. This is my distance D3. So can I find a unique point? If I give you distances D1, D2, and D3, is there a unique solution to this system? This is distance D1, this is distance D2, and this is distance D3. How many points are there that are D1 from A, D2 from B, and D3 from C? Is there a unique point? No, I have 2 points, right? There's these 2 points are both satisfying these system of equations. So should we expect a unique solution to this system of linear equations? No, right? And is the math telling us exactly that? Right? It's saying that if you set up your least squares problem, you're not going to be able to find a unique solution because you set up your measurements poorly. Right? It's saying if you put your beacons, if you put your satellites in a two-dimensional problem exactly along the line, you're toast. You cannot figure out where your receiver is. Right? In a three-dimensional problem, again, if they're on a lower dimensional space, there it'll translate to being in a plane. So you need to basically have your distances be sufficiently different from each other. Your measurements need to be sufficiently different so that you can actually solve, right? So yes, we did some theorems about some null spaces and we tried to show when something is invertible or not. But it actually matters, right? Because if you didn't know to check for this, you could say, oh, I'll put them all in a line so everything will be nice and symmetric. And then your multi-billion dollar GPS system will not work. So don't do that. But does everyone see what the issue is here and why this is a bad idea? Okay? Any questions about this? Okay. Great. Okay, I'll wait for another minute. Ask your friend a question about it. Talk to your neighbor, make sure we're all on the same page in terms of what's going on. Would it help to add more beacons exactly on this line if I had another D here? Still wouldn't work, right? Any questions, anyone? Anyone? We're all good? Let's move on. Question? Yeah. Great question. The question was, what if instead of having these two intersections, we had two circles that were just tangent to each other, right? You're thinking about something like this. Right? So in that situation, you would be able to get this unique solution out, but it would be by chance. Like, this is not the typical situation that you're going to expect. Like, this will actually never happen because especially because you have these noisy measurements. So you'll never actually experience this in real life, but in this one case, things would work. Yeah, good question. Of course, that wouldn't mean that your matrix is going to be invertible, right? Your matrix is still not going to be invertible, but your observations will be such that you will still be able to recover. This is more something saying about what your D1, D2 measurements are than it is about the placement of your beacons. Yes? Is there a way to figure out what a good beacon placement will be other than just if you don't put them in the line? Well, the question is, so just for everyone here, is there a way to figure out what a good beacon placement would be other than making sure that they're not in a line? So you will see that you want to, anytime you put beacon placements, you want to write this matrix out and see how easy is it to invert A transpose A. We will see, basically, if you know that, you will see that if they're in a line, they will not be invertible. It turns out that's basically the only way that they're not going to be invertible. We're not talking about it in this class, so it's a little bit out of scope, the answer I'm giving you, but there is a notion of how easy it is to invert a matrix. And you'll come to talking about this when in 16b, when you start talking about singular values. And you will want to make sure that basically it's easy to invert your matrix, in that you have your singular values away from 0. But, you should be able to basically write this matrix and check that, but that's out of scope for 16A. You'll see it in 16B. Good question, though. Any other questions? I'm really liking this. Like, people are asking questions. It's much, much nicer. Okay, should we move on? Yeah? Okay. Let's move on. So now, I want to introduce the new part of today's lecture, orthogonal matching pursuit. And here we're going to try and solve basically an even more complicated GPS type problem. So let's say, you deploy, you do the lab from Module 3, you deploy a fabulous GPS system, you can track the location of your cell phone wherever you are. And you have these gold codes, right? These gold codes are these amazing tools. They're these very nicely designed codes so that you can have these signatures, you can transmit them. Even if there's multiple transmissions, you can still figure out which gold code is being sent. But you want to now adapt this system to being something closer to home. So you're at home and you want to build a smart home. You want to have, let's say, you walk in the door and your lamp is maybe transmitting to you. You want to have your television transmit to you. You have some kind of smart device that triggers as soon as you walk in. You want to have your, stove know that, okay, you want to start making dinner. You want to have, your peanut butter to come out of the fridge so that you can make your sandwich. You want to have your plants have some kind of smart irrigation system that, you want to have it, you want it to detect that, okay, there's not enough water. You want to measure what kind of moisture there is in your garden and have it be transmitted back to your cell phone. You have hundreds of thousands of millions of, let's say, smart devices throughout your home, right? This is a vision that many people are selling, and it's a different question of whether or not you want to be that interconnected within your own home. But if you think about this even more at a larger scale in terms of in manufacturing factories, or where you have a large number of automated devices that are simultaneously doing things, you want these devices to be able to automatically communicate wirelessly with, let's say, some kind of central base station to give status updates, right? Or to raise flags, like, okay, I'm broken, please come repair me. Whatever it is. And it seems like some of these ideas that we've been discussing that allow for these signatures to be developed might be useful here, right? And what we want to try and do is we want to try and say, can we extend the ideas that we've been building out for developing the GPS system to solve this even more complicated problem of, millions of billions of devices that are all talking at the same time. Think of basically automated traffic management, environmental sensors everywhere. Think about, many, many different potential applications for this. Some of you may have heard the phrase the Internet of Things, where you have a lot of different devices that are doing the talking. So this is kind of a step in that direction. Question? No. So this is the vision that we're really trying to enable. So let's say you want to build this smart home, and you want your clock to be talking to you, and your television, which doesn't have an antenna anymore, but your lamp maybe. All these different devices, right? They're all transmitting, and or you want to say, well, how do you figure out which devices are transmitting? And let's think of a situation where you have tens of thousands of devices everywhere. It's not one, it's not two, but it's really every little thing. Think about, your clothes are labeled, your shoes are labeled, your pencils are labeled. Everything is trying to talk to you, potentially. It's trying to tell you about its status. How do you actually handle this? It's a pretty complicated problem. Again, like the GPS problem, we're not going to be able to solve every single part of this problem, but we're going to make some steps to try and solve this. So before we jump into the kind of algorithmic approach we want to take for this, why don't you take a minute to see how we might be able to use some of the tools that we've built up so far in the semester to be able to address this problem. So, think on your own, feel free to talk to your neighbors, whatever you want, but see how you might want to try and engineer this. Okay, so any ideas that people might want to share about how to go about this problem? Someone who hasn't spoken yet. Yes, but yeah. Can you have really, really long gold codes? Great idea. We will definitely be using really, really long gold codes. So, yes, that's definitely a big part of it. We want to use gold codes and we want to use long gold codes. Yeah. Yeah, you want to have a lot of transceivers in your house? Yep, you will have. You can do this even with one, though. So what we want to do is, let's say you just have one, and you want to go with that. At the back there, the green shirt. Yeah. Okay, yeah, excellent. Good suggestion, yeah.
What if you had a 10,000 dimensional vector, and each one was orthogonal to each other one?
Yeah, we could definitely try and do that, and we kind of want to try and do that, but we'll see if we'll get there. Yeah. Yeah. Yep, this is basically what we're going to do. This is basically the same idea of gold codes, and we're going to use the idea of modulation, which you looked at in homework 12. So we're going to have a signature, but instead of having a signature at the beginning, we're going to code on top of it. So we're going to multiply our signatures by different numbers and have these periodic repeating signatures that basically can have us solve the problem. Okay, so this is exactly the direction that we want to be thinking in. So we want to build on the idea of gold codes. right? So I have my gold codes. These are signatures, SA, SB, for example, for the different satellites. And what we know about gold codes is that the inner product of SA and SA is pretty large, right? In fact, if we have plus minus 1 gold codes, this would be equal to n, which is the length of the vector. And we know that SA inner product SB, this is very small, right? These are almost orthogonal. So what we're going to do is we're going to say, okay, let's give every single device a signature. Let's give this device signature SA. Let's give this device signature SB. Let's give this device signature SC. And yes, ideally, we would want to have these really, really long signatures, right? But that might be quite problematic in terms of computation, and that's a lot of signatures to generate. So let's stick to our gold codes being of length, 1023. Which still gives us a lot of different unique signatures. But let's say now we have some more structure in our problem. So let's say we have our received signal. We have, each of these is transmitting, and they're transmitting, let's say, their signatures. Right now, let's start with a simple problem of just detecting which devices are on and which devices are off. So let's say that when a device is on, it is transmitting its signature. When the device is off, it's not transmitting its signature, right? Something pretty straightforward. So let's say that I have some received signal R, and this is maybe some constant alpha 1 times the first signature plus some constant alpha 2 times the second signature plus some constant alpha 10,000 times S 10,000. Okay? Yes?
Is there a limit to how many orthogonal gold codes we can generate with length 1023?
Yes. The question is there a limit of how many orthogonal gold codes we can generate of length 1023? The answer is yes. And this is exactly why we're going to be taking the approach that we will be taking. Is we could have an arbitrary number of them. Well, so you can count the number of plus and minus 1 sequences. And the tools to answer that question, again, require classes like CS70 and beyond, so we're not going to answer that question, but it's important to know that there's a finite number of gold codes that you can generate of a certain length. Yes?
That limit would be above 10,000.
What?
The limit of number of gold codes
would be below 10,000.
below 10,000.
Oh, sorry. Okay, I didn't actually do the math on exactly how many these numbers are. Think of, instead of 10,000 devices, 1 billion devices. Like, we're thinking very, very large number of devices. Yeah. Good question. Yes. If you could generate 10,000, if you had 10,000 unique signatures, you could do something different. But, so here we're assuming that there's a unique signature for everything. Let's not worry about exactly how to generate each of these signatures. Let's assume that there's enough unique signatures using the gold codes of length 1023 to label all of our 10,000 devices. The exact math on figuring out how long the gold codes need to be is out of scope, so I want to avoid talking about it. But excellent question. Thank you. Okay, so we have this received signal, and we want to basically figure out, what these alphas are. Most of them are going to be zeros, but some of them are going to be on, and we want to figure out what those are. So we can write this basically as a matrix equation, right? So if I put all of my signatures in a stack, S1, S2, all the way up to S10,000, these are my vectors, times, so let's say this is now a length, there's 1023 is the number of rows, and this is 10,000, times my alpha vector, so this is alpha 1, alpha 2, alpha 10,000, which is equal to my received vector, right? And my received vector is of length basically 1023. So this is my R vector. Yeah? I'm sorry, I didn't understand. Yes, the set of alphas represent the modulation, but here we're thinking of even something simpler. Let's say a lot of the alphas are just zeros. So the alphas are some small number if the device is on, and you can think of it as modulation. It doesn't even have to be that. We just want to figure out which ones are transmitting and which ones aren't. Good question. So when we look at this A matrix, right, is this A matrix like the least squares matrices that we've been thinking about? What is its shape? The least squares matrices were very tall matrices, right? Lots of equations and few unknowns. Here, we have essentially 10,000 unknowns, these alphas. And we have far fewer equations in comparison, right? We basically have the length of the gold code is the number of equations that we have. So yes, we've set this up as a kind of, matrix equation, but how do we want to solve it? Right? Can we use the standard least squares type technique here? How many solutions do we have to this system of equations? We have far fewer equations than we have unknowns. So very few constraints, lots of free variables. When you do Gaussian elimination on this, what are you going to get? Infinite solutions, right? Like if you had a system with 2 equations and 10,000 variables, there's going to be an infinite number of different ways of satisfying these, right? So it turns out that, yes, you have a lot of equations, and yes, you have a lot of variables, but you can't actually, figure out exactly which ones are transmitting. So we cannot use our standard, again, we're in a situation where our use Gaussian elimination when you have a matrix equation strategy doesn't quite work, right? First of all, this is not a square matrix, so we cannot invert it. Yes, there's going to be noise present, but we don't even have so many equations that we can use the extra equations to reduce the noise. So we had to come up with a third new kind of technique. And this technique is called orthogonal matching pursuit. And the fundamental idea behind how to solve this is to be greedy. What does that mean? Being greedy means we want to look at what we're receiving and we want to say, well, what's the most important component here? How can I explain this received vector maximally? And by trying to do this, I'm going to be able to one by one extract out my signal. So let's start, playing with this a little bit. Let's say I have I have these, but I have only some small number of things that are transmitting. So I have R is equal to SA plus 2 times SB. Let's say I have this, right? If I wanted to figure out which signals are in SA, or what are in R, how would I do that? I know something about inner products, right? And when we had basically the GPS problem, when we had a received signal and we wanted to figure out which satellites were transmitting, what did we do? We did a cross-correlation, right? And we did a cross-correlation, and he said that, well, if the cross-correlation was high enough, then we say that the satellite is transmitting, right? And if it's not high enough, we say that the satellite isn't transmitting. So would it make sense to use some kind of idea like that here? Right? So what we want to say is that, well, let's consider the inner product of R and SA, the inner product of R and SB, the inner product of R and SC, and R and SZ, and R and whatever, S. Okay, now I've done an alphanumeric numbering scheme, but you understand what I'm saying, right? We consider all of these inner products. Okay? What do we expect to happen for most of them? Get a very small number, right? Because those aren't present. If R was basically this linear combination of SA and SB, which ones do we expect to be large? SA and SB, right? So we expect these to be large, and then we want to say, well, okay, let's say that we have some large inner products and some small inner products. We want to go one by one and say which inner products or which signals are the ones that are present. So if I look at all of these inner products, which signal is the most likely to be present, given just the correlations or these inner products? I want to look at these values, right? If let's say the inner product is really, really large, then that's probably a good candidate for that signal being there. Then what I can do is maybe I'll say like, okay, let's say I get a large inner product with something. I take that signal, remove its effect, and then try and search for the next best thing. So what we want to do is let's write it out. So let's say consider all the inner products find the maximum inner product. Let's say the maximum is with some signal S max. We say, okay, our guess is that S max is transmitting. Okay? So we say, okay, we can explain some part of R by assuming that S max is transmitting. So now we want to remove the contributions of S max from our received signal R, right? We know that this R is a linear combination of each one of these vectors. So I want to go basically choosing the vectors one by one. So if I go through this and I say, well, okay, it has a really high inner product with, let's say, SA, I'm going to take SA out and then say, well, let me now rinse and repeat. And so how do I remove a component? I say basically project R onto S max. So basically I want to consider the projection onto S max of R. Right? I have basically some R. I have some S max. I'm going to take this projection and say, well, this component of R is explained by the activity in the direction S max. Right? Let's figure out where the other parts are coming from. So I do this, and then I say, let me consider my R nu is equal to R minus the projection of S max or of R onto S max. And now I have a new vector, right? So basically I take my error vector, this is my error vector. This is what I'm calling R new, which is what we call the error vector in the least squares or the projection setup. And I say, well, my R is basically this part along S max plus this other component that is orthogonal to S max. So I can explain some of R by looking at S max. Let me explain the rest of it now by doing this again. So once I have this R new, I basically go to the beginning. So I say, okay, let me now consider inner products of R new with all of the signals. Let me pull out that signal that has the biggest inner product. Once I pull that out, I say, well, I've explained some part of my signal now. Let me move on to do this one by one by one. And what we can do is by saying that because we know that most of these alphas are 0, I can keep doing this one by one until, let's say I know that at any given time, probably only 2 or 3 things are transmitting. I can do it for the first 2 or 3 and then stop. This is the OMP algorithm, orthogonal matching pursuit. It's just an introduction. We're going to go into it in much more detail in lecture next week. But this idea is basically this idea of peeling off one component by one component. When you don't have enough equations to instantly solve the system, you say, well, let me take my best guess. Once I have my best guess, great, I take that aside, and let me go to the next step. So I want to just show you this in an example so that you have something that you can ground to. And then we'll end for the day. So I'm going to go through this notebook pretty slowly, but I think it'll help illustrate what's going on. Yes? Great question, right? Why are we subtracting the projection onto S max as opposed to just subtracting S max? Because we don't know these alphas. So these alphas might be exactly 1, in which case this projection will also turn out to be exactly 1. Alternatively, because there might be some attenuation along the way, or because you're choosing to, amplify your signal, alphas could be non-1 numbers. In which case, you would actually choose to do something that isn't just, you would be better off subtracting the projection.
So if SA and SB were projecting, I guess my question is, what are we keeping track of to know that those, it seems that we just keep throwing away R old and then R new keeps coming?
Yes, we will keep throwing away R old. We have our received signal. We always keep track of that. And you'll see in just a minute. After this, maybe your question will be answered. So let me just show this. So I'm not using, real gold codes. I'm just using very, very simple signatures. So let's say we have 3 signatures, 1, 1, 1, 1, minus 1, 1, and 1, minus 1, minus 1, right? So I have a received signal. I'm just making this signal up for my demo, but in reality, we would not know this equation, right? I'm just making this up. So I receive, all I see really, I don't see anything in this box, all I see is this. That this is what I received. So now what I'm going to do is I'm going to say, let me take the inner product of this with SA, and I get 5.6, right? I take this R dot SA. Everyone with me here? Then I take the inner product of R and SB, and I take the inner product of R and SC. Now that you see these inner products, which is the strongest signal that is present in R, based on just looking at these inner products, not looking at R? SB, right? It has this giant inner product. So you say, well, my guess is that B is transmitting. So what I'm going to do is, let's say I know that B is responsible for some component of A. Well, I'm going to say, how close can I get to R by moving along this B, right? And the closest point along B to R, we know how to calculate that, right? That's just the projection. So I know I can only explain so much of R by B because it's not just B. There's other stuff as well. So what is the maximum amount I can explain? Well, that's given by the projection. So this is related to the question that was asked earlier, which is why are we taking the projection? Why aren't we just subtracting this out? Because SB itself is just a direction, and you want to figure out exactly where along that direction you want to be. So this is the projection, and I subtract it out. Well, what do I get? I get this coefficient 2.4, right? What was our actual coefficient? It was 2. So I got this coefficient 2.4. Now I'm removing 2.4 times SB from my R to get my new R. Okay? Everyone with me? Okay. Now I have a new R. I've already explained some part away. I have the rest remaining. So I say, okay, let's try again. Now who else was talking, right? I already explained away the part of B. So let's take the inner product of the new R and SA. Okay, I get something. Inner product of new R and SB, what do you get? Basically 0. Right? Because we've already explained away all of the part of B. And SC, I get this number. So clearly SA is now the loudest person, or the loudest thing. So now I know that both SA and SB are speaking, right? So now, if I have a direction SA that I can move in, and I have a direction SB that I can move in, what is the total space that I can move in if I have two vectors? It's the span of these vectors, right? Or if I put these two vectors as the columns of a matrix, it's the column space. So now, instead of projecting just onto SA or just onto SB, I'm going to say, how well does the combination of these vectors explain my actual received signal? And so I'm going to take the projection not onto just SA or SB, but onto the span of SA and SB. Okay, this is an important point. So I'm basically taking the projection. So this A is basically SB and SA stacked together. I'm taking it both. Does everyone see what's happening here? So this is now A is just SB and SA stacked together. And I'm going to project R onto this combination. And what do I get out as coefficients? I get the coefficient of SB is 2, and the coefficient of SA is 1.2. So I've refined my estimate, right? Like I recovered this 2. The last time when I just did the first iteration of the algorithm, I got a 2.4. But here, remember, our actual signal is 1 times SA plus 2 times SB, and there's some noise. So we don't expect to recover everything perfectly. We only expect to recover things approximately because there is noise at the end of the day. But we've gotten these 2 points. And now we can keep doing this over and over again. Question?
Why did A end up having a size of 3 rather than 2 by 2? You're stacking 2 vectors.
I'm stacking 2 length 3 vectors. Yeah, because my SA, SB, this is SB, SA, and this is SB. So I'm stacking those. Yeah. Yes, question? No, I just did that because I first found SB. So my first entry was what I found first. Second entry was what I found second. You would get exactly the same answer if you stacked them in any other way. You would just get the arguments reversed. It's just that, you stack the thing you found first. What does a negative inner product mean? Inner product can be positive or negative. It doesn't. Here you want to look basically at the magnitude of the inner product. Yes?
How do you know when to stop doing the iteration?
Exactly. How do you know when to stop, right? this is the most important question, and there's multiple answers. I will answer it in detail in next lecture. So, yeah. But for now, you can say, if you know how many devices are transmitting, after you've picked out those many things, you can stop then. But with that, I will end. Hope you all have a good break. Rest, sleep, stay healthy, and you just have a little bit for the end of semester, so stay strong. Use this time to just recharge, and you have one more week.